To see through your own questions, to understand the realities around you, to participate in an adventure of discovery. You are surrounded by answers. And the question is, do you have a question? Do you have any questions at all? For often, as important as answers are questions. Shall we ask a question? What is nature? What is nature? We all have our own perceptions of it. This is the way a curious artist might assemble nature's shapes and colors, discovering and communicating an interest in nature. But when another with curiosity, a scientist, observes nature, the arrangement might be somewhat different. Now I wonder why that is. Both artists and scientists are indeed curious about nature. Both in their own ways interpret nature, seeking underlying truths behind the mystery. Scientists measure precisely, record and classify, look for orderly patterns. And, having found a pattern, use it to predict a cause and effect relationship, contributing knowledge about nature, useful for mankind. From many patient observations, a creative mind will glimpse a pattern or form a hypothesis, which then must be proven by more observations, measurements, and evaluations. And after looking quizzically at nature, a scientist today can use a computer to help find a pattern, if it's lurking somewhere. The granddaddy of modern experimental science had a great curiosity about nature. Galileo started a trend.
Turning to the great volume of nature is the way to make one look high.
He wanted to find out something about gravity. So he tried an experiment.
Will the heavy object reach the ground before, at the same time, or after the light object?
A scientist observes an event, writes it down to better remember it, to compare it with the memory of other events, to see if they will form a pattern. A scientist is very curious about what happens and why. And seeing many things happen, needs a kind of shorthand to express concisely what's been observed. Of course, science does have a special language for this, mathematics. It's an ideal servant for remembering, for comparing, for understanding, for communicating. In its own right, mathematics is a whole science. And what a lovely, symmetrical, dependable language it is. And here we are again. Why, when confronted by a natural event, does the scientist react differently than, say, the writer, or artist, or musician? Here's another illustration which may help us. Consider this natural phenomenon. Communications. What we're doing right now. Transferring information from one place to another, from one person to another. It's a natural phenomenon like flight, time, heat, color, and magnetism. The curiosity about the transfer of information might have been what led the painter Monet to his series of studies of the quality of light. A writer, James Joyce, created this book, an experiment in the stream of consciousness of a human mind, put into writing.
Too much old chat in it about politics and earthquakes and the end of the world. Oh, let us have a bit of fun first. God help the world.
A mathematician, Claude Shannon, while working at Bell Telephone Laboratories in 1948, published a mathematical theory of communication. This theory has its own drama, poetry, design, and vision. And, like the painting in the book, it is a description of the reality of a natural phenomenon, as Shannon saw it. We're going to be acting out the information theory for you, because it's more fun than a chart. Because I understand it better this way myself.
I'm the source, where the flow of information starts. All communication systems have a source. A source might be a person talking, a bird calling to its mate, a computer, or a radar tracking an aircraft.
I'm the encoder transmitter. In our simplified demonstration, I take the message from the source, encode it into some convenient form for transmission, and send it on its way.
As the receiver decoder, I take the messages out of the channel and decode them for the destination.
As the destination, I react to the content of the message.
These slips of paper represent the transmission channel. In other systems, the channel might be a pair of wires, a ray of light, or radio waves in space. In this example, the letters blur when written on blotting paper. This interference with the message in the channel we'll call noise, static. All channels have it, and it's unpredictable.
Suppose I try to send twice as much information in the same amount of time. Will this increase efficiency?
That won't work. The blotting paper will blur the small letters. There'll be too much noise, too much static. The receiver won't be able to understand.
Suppose I try to send 3 times as much information in the same amount of time.
A simpler way is to code the letters so that the transmitter need only put a dot for 1 and leave a blank for 0.
Through many experiments, the mathematical theory of communication was developed. It described for the first time the relationships between the parts of a communication system and how to code only essential information for transmission. It's a thinking tool being used today for better understanding of information and transmission. Or think of it this way. If information were water, Shannon's theory tells us how big and how good the hose has to be. Curiosity about why things happen as they do has led us to make a channel better fit a message.
Aloha.
Someday, the information theory may rank with the discovery of the vacuum tube and the transistor in its contribution to communication. And I can't help thinking how lucky for us there are those like Claude Shannon, whose curiosity about nature leads them down practical paths. Behind this childhood toy is a common, well-understood natural phenomenon. Science has observed, measured, and classified magnetism about as thoroughly as any force we know. Magnetism can be observed as it affects bits of iron in sand. It's a force that continues to yield new dimensions, new revelations. One such revelation, magnetic bubbles, is a good example of science finding new circumstances in which predictable patterns occur. In the late 60s, research was begun with very thin sheets of special magnetic material.
What's special is that the lines of magnetism in these tiny sheets only go up and down, perpendicular to the plane of the thin sheet. Under a microscope, the magnetic areas can actually be seen with the help of polarized light. The wiggly lines are the areas of the same magnetic direction, or magnetic domains. Now, bring a magnet close to the thin sheet to boost either the ups or the downs, and indeed one side does get larger, and then the domains can be made to snap into circles. We've called them bubbles because of the way they look under the microscope. Tracks or patterns of metal can be printed on the thin sheets to guide the bubbles and act like shelves for storing them. With the aid of more magnets, the movement of the bubbles can be controlled.
Consider each bubble a bit of information. Think of a bubble as 1, the absence of a bubble is 0, a binary number system. When the magnets pull the bubbles past a counting device, they register as numbers. Because the bubbles are so tiny, a combination of 14 of these tiny sheets can store well over 1 million bits of information. When the watching and measuring and evaluating are done, nature rewards the curious with new information, provable, repeatable, and something of value to mankind. How much does science really know about our world? As one great man, Isaac Newton, put it,
We are still like children, playing with pebbles on the seashore as the great ocean of truth rolls on unexplored, beyond our reach.
the secrets still locked in these walls of rock dwarf the knowledge man has been able to collect. Research has not fully unraveled the secret of life, and may never. Long after our questions may have ceased, the stars will continue to shed their secrets on the earth. When will we learn all we need to know, or will we ever? We have learned to thrust ourselves through space, but unfortunately people have not learned enough about human nature to stop the possible misuse of knowledge. Despite our curiosity, are all the answers within the grasp of science or technology? Science or technology, there is a basic difference. And to be realistic about achieving goals, we should understand the distinction. For example, when the moon trips were first announced by President Kennedy, he knew we would succeed, because science was no longer the key to the completion of the program. Enough basic scientific questions about how to get to the moon and back had been answered. What still had to be solved were the technical questions, materials, design, engineering, and a massive effort by thousands of brilliant, creative people would and did bring success. But let's consider another goal, conquering cancer. These destructive cells. Why won't a similar multi-billion-dollar mass effort bring predictable results in a predictable time? Because why cancer happens has not yet been fully answered. All the science is not yet known. Putting twice as many people on a scientific task will not ensure it's being done in half the time. A scientific breakthrough, a discovery is needed. In simplest terms, science asks why. What happens? In the middle of the last century, a great scientist, studying natural phenomena, made a major contribution which changed the pattern of our lives. James Maxwell, a Scottish scientist, after tirelessly making exact mathematical descriptions of electric and magnetic fields, predicted that light was electromagnetic, not mechanical in nature.
The line of force from the sun spread out from him, and when they come near a planet, curve out from it, so that every planet diverts a number depending on its mass from their course.
His revelations led to better understanding and ultimately to the discovery of radio waves, which has made much of today's mass communications possible. Most importantly, Maxwell's mathematical genius helped us understand that visible light, radio, and other radiation were all part of the same spectrum. By the late 1940s, they found that these waves, just longer than infrared waves, could be carried in hollow tubes. While the science for millimeter waveguide tubes has been known for 30 years, the knowledge has been banked. Here is an example of technology being in no hurry to exploit what science has discovered. Only now, when today's avalanche of data has created a need, has the communication system moved out of a laboratory. The diligent work of many people has created a system that can transmit almost 250,000 simultaneous phone conversations, or when coded into pulses of digital information, the equivalent of this 20-volume encyclopedia could be transmitted coast to coast in an instant, like this. Optical fibers hold another great promise for the future of communication. Using light itself to carry information is another possibility now under practical consideration. Light is projected through tiny glass fibers. Each fiber is only a few thousandths of an inch in diameter. And because of the high frequency of light, it can carry a vast amount of information. We are not completely sure just how the human eye changes light and color into images for the brain. We know it works better than anything man has yet invented. And so, perhaps instinctively, we use the eye as a model. Here's a fascinating example. Remember the magnetic bubbles? At Bell Laboratories, they're investigating an electronic equivalent of the magnetic bubble. It's called the charge couple device. And like the magnetic bubbles, it may be used for the storage of information. An extraordinary thing about the charge couple device is that it also has imaginative possibilities as an image device for making electronic pictures. It works something like the human eye. In the eye, light falls on nerve ends called rods and cones, which, point by point, transmit impulses along the optic nerve to the brain. In the charge couple device, at each point on the picture, light creates an electrical charge. A lot of charge where the light is bright, no charge where the point on the picture is black. The charges, each carrying information about one point of the picture, are moved out, one after the other, and at a receiver, changed back into points of light that make up the picture again. Charge couple devices may someday revolutionize how television cameras and video telephones see. They also can have major impact on information storage and communication switching devices. Some of our most basic questions about nature have yet to be answered. What actually happens at the instant a photon of light strikes a molecule of chlorophyll in this leaf? Or when light excites any other molecule? What is happening in such an excited state of matter? Answering the question is a contribution to the bank of knowledge that science and technology will one day draw upon. With every scientific discovery, with every technological solution, we gain increasing respect for nature. We can better understand, we can direct, but we cannot change nature. As the painter paints, as the writer writes, so does the scientist create and communicate his understanding of reality. The medium is different, but the personal rewards of art and science are remarkably parallel.
A scientist has to be somebody who tries to understand the real world or understand the world.
Scientists are basically craftsmen that get their pleasure and their reward out of the work they're doing, and they are not necessarily competing so much against other people than against their own brains.
Science is probably more open to people of every sort. It's probably a profession that people are judged really on their merits than almost any other profession.
In the scientific field, it's not who you are or how old you are, it's always how well the work was done.
For us, it's just the excitement of discovery and the hope of finding that you had a really creative idea that ultimately works out. That's the thing that really keeps us moving. Attitude of questioning things, trying to get your answers in an objective manner and observing what you see.
If they're really curious, that would be the most important thing.
Science people are aiming to gain understanding of why a thing happens.
The scientist is closer to the real thing than other people. They're a little bit more part of it and have a little bit more understanding of what is really going on.
I would think that scientists are creative people, just like artists and so on, and need a lot of imagination in order to be good scientists.
One thing is sure. Patience and perseverance are qualities needed in a successful pursuit of science. Some problems yield only to long sieges. And there are people who patiently spend years attacking old problems. Indeed, these are frequently the key positions of greatest value in the search for new knowledge. Such a quest was followed by Brattain, Bardeen, and Shockley. Their discovery of the transistor was no accident, but was a product of a decade of careful, thoughtful, purposeful investigation for something better than the vacuum tube. Sometimes science yields to fortuitous accidents. So if your mind is prepared to recognize the value of an incident, you can reap the fruits of a great spillover, that single flash of intuition, the thunderclap of insight. The concept of magnetic bubbles actually spilled over into an idea for a similar electronic invention. And in an hour, the concept of charge-coupled devices had been chalked on a blackboard. Patience, discipline, intuition, the joy of discovery. These are all part of adventure and understanding. does not pretend to have all the answers. But the search can be as exciting as the achievement. Sometimes, without recognizing them, the answers can trickle through your fingers. Or, if you recognize it, you may hang on to a grain of truth. In fact, a grain of sand. Silicon dioxide was the key material in making transistors adaptable to a wide variety of applications. So, if you have an appetite to discover, to contribute, keep curious. Look everywhere, and remember this valuable clue. It's a clue revealed 400 years ago by Sir Francis Bacon, who had this to say.
Things not yet invented will be discovered by ways not yet thought of.